In this video, I'll introduce another important model of growth, the logistic model. I'll show you the model and make connections to prior ideas from this course. Then I'll share applications of the logistic model to both population growth and resource use. In the previous video, I shared how we can think of the logistic model from the perspective of flow. A logistic model arises when the net flow can be described as proportional to the product of the stock level and the difference between the stock level and the carrying capacity of the system. Another approach is to describe the logistic model in terms of relative growth. Recall that an exponential model represents constant relative growth, say 3% per year. The logistic model, on the other hand, describes situations where the relative growth rate falls linearly as the stock level increases. The graph shown captures this idea. Stock levels are plotted on the horizontal axis, and their relative growth is plotted along the vertical axis. The exponential model is represented by the green horizontal line. Whatever the stock level, the relative growth rate is the same. The logistic model is displayed in blue. As stock levels rise, the relative growth rate decreases. This reflects the idea that as a quantity approaches its limits, it will not grow as fast. Here's an example where we can see this perspective on the logistic model in action. The table shows U.S. population in millions from 1790 to 1940. Notice that the data is every 10 years, since this is when the census occurs. I've also computed the decade-to-decade relative growth rate for this data. For example, to get the first entry, I computed 5.4 minus 3.9 divided by 3.9 to get 0.385. In other words, the decade-to-decade growth at this point was 38.5% per decade. The plot shows the relative growth rate on the vertical axis and the total population on the horizontal axis. Notice that the relative growth rate is decreasing over time, following a roughly linear path. This indicates that the data roughly follows a logistic model. One of the powerful things about this perspective is that we can use it to estimate the rate constant and the carrying capacity for a data set. To start, notice that the relative growth rate is the flow, or the absolute growth rate, divided by the stock. If we use the formula for logistic flow we've previously derived, then we see that the relative growth rate is R times 1 minus S over C. When S is 0, the relative growth rate is simply R. In other words, R is simply the intercept on the vertical axis. Also, the relative growth rate is 0 when S is equal to C. This means that the horizontal intercept is the carrying capacity. Let's apply this to the U.S. population data. I used Excel to add a trend line to the scatter plot and to determine the equation of this line. The y-intercept is 0.37. This is the rate constant. In other words, in 1790, the reported U.S. population was growing at roughly 37% per decade according to this model. We can also solve for the x-intercept by setting y equals to 0. So we get that x is equal to 0.3706 divided by 0.0024, which is equal to 154. This is the carrying capacity C. That is, the logistic model predicts a carrying capacity of 154, or a maximum population of 154 million people in the U.S. Of course, we know that the U.S. population is well above this. This logistic model is a good fit for the data through 1950, but then starts to badly underestimate the population. Of course, beginning in the 1950s, the U.S. experienced a population explosion known as the baby boom. The fact that the logistic model failed to predict this highlights that the baby boom was in fact a radical change from earlier population dynamics in the U.S. Recall that the logistic model is determined by the initial stock S0, the rate constant R, the carrying capacity C, and the time step T. In the previous example, I showed you how to use data to estimate the rate constant R and the carrying capacity C. Once we have this information, we can also estimate the time to peak flow using the formula below. Let's look at an example where the peak flow is particularly important. The table shows U.S. crude oil production to date in billions of barrels from 1931 to 1950. For example, the U.S. had produced 13.8 billion barrels of oil in all years prior to 1931. I've also computed the year-to-year relative growth rate for this data. To get the first entry, for example, I computed 14.6 minus 13.8 divided by 13.8 to get 0.058. The plot shows the relative growth rate plotted against the total oil production to date. Note that the relative growth rate is decreasing over time, following a roughly linear path. In other words, a logistic model makes sense in this scenario. I've included the trend line on the plot along with its equation. From this, we can determine that R is equal to 0.0693 and C is equal to 0.0693 divided by 0.0004, which equals 173. In this scenario, the carrying capacity represents the total U.S. oil production. So this figure predicts that the U.S. has the capacity to produce 137 billion barrels of oil. Now let's compute the time to peak flow. Using S0 is equal to 13.8, we get that the number of time steps is equal to the log of 173 divided by 13.8 minus 1 all over the log of 1.0693. This comes out to be 36.5. In other words, this model predicts that the U.S. peak oil production would occur in approximately 1967, 36.5 years after 1931. In fact, U.S. oil production peaked in 1970 and then began to fall. Some believe this was partially responsible for the 1973 oil crisis in the U.S. Since then, U.S. oil production has grown again due to new innovations in oil extraction. Peak flow for world oil has also been an important economic issue in recent decades, although new extraction methods have eased economic concerns that the world may experience peak oil.